Ginger Gilsdorf is a software engineer at Intel. She focuses on enabling database and analytics software vendors to run best on Intel data center platforms. Her experience with persistent memory include investigating possible use cases, developing software that takes advantage of persistence, and optimizing for performance. Let's hear from Ginger Gilsdorf on accelerating analytics workloads with Alluxio data orchestration and Intel Optane persistent memory.
Great, thank you, Jasmine. Okay, I'm going to go ahead and share my screen. And I will assume you can see everything and hear everything unless I hear differently. So like Jasmine mentioned, I'm happy to be here today, and I wanted to come in and discuss some of the work that Alluxio and Intel have been collaborating on, mostly around our Intel Optane persistent memory. As a software engineer at a hardware company, I find this quote very helpful, and I believe I'm attributing it to the right person, but in a sense, hardware without software just generates heat. And then software without hardware is just ones and zeros. So the thing I really like about my job is that I get to see the interaction of the two and really analyze what's going on and understand how things work together. So that's kind of the guiding principle of my talk today. And in the agenda, in the simplest terms, I want to go over the hardware, give you a little bit of background and understanding of these different technologies I'm mentioning, go through the actual software, and by that, I'm focusing on, of course, Alluxio as the data orchestration layer, and then a specific workload that we've done some testing on. Show you the results, and then a little bit of analysis so that we can understand what's going on in both the software and the hardware. So let's see, starting with the hardware. I promise I won't give you all marketing slides, but I did want to give you a bit of understanding of the latest Intel Xeon scalable processor. If you've heard code names, this is Ice Lake. Ice Lake has launched. It launched actually back in April. It's available in the market. You'll see, of course, cloud availability is coming. Different CSPs are at different schedules or different adoption cycles, but what I see right now is that things like, I think Oracle has some instances available, and then I know that Microsoft Azure has some private preview instances available. But on that note, just stay tuned and communicate with your CSP if you're looking for these instances in the cloud. And then just to give you again some more background, a comparison between our second generation, which came out in 2019. That one was called Cascade Lake. And you can see that we've upped the maximum core count from 28 to 40. It's a pretty big impact there. In terms of memory, we've added more memory channels and now support memory running at 3200. The Intel Optane persistent memory line. With Cascade Lake, we launched the first generation, the 100 series. With Ice Lake, we now have the 200 series, which is called Barlow Pass. I'll give you some more details on that one. And those do need to stay together. So for example, if you were using a Cascade Lake CPU, you would use Apache Pass persistent memory. And then Ice Lake, you would use Barlow Pass. And one big impact is that PCIe, we've now adopted Gen 4, so that can make a lot of impact on certain workloads. And in terms of performance, if you're moving from Cascade Lake to Ice Lake, we've done a bunch of the industry standard benchmarks and come up with this average number here. And of course, your performance may vary, but in general, you're seeing a pretty good increase in performance. There's a link there if you want to look into the details of these benchmarks of where we got that number from. Okay, the Intel Optane family, there's a lot of terminology and some of this can get a little bit confusing. So I wanted to make sure that everyone understands which form factor I'm referring to when I speak about these different components. The Intel Optane technology is actually kind of an umbrella term that we use to refer to the underlying media, which you might have also heard of 3D Crosspoint. That's the former name for the media that we co-developed with Micron. Now that we've kind of split things apart, we have that back under the Intel Optane name. That's the brand new memory media technology. It is not transistor based. It's a different technology. And then with that technology, we have, of course, the controllers, some interconnect IP, and then the software that supports all of this. So this is kind of the big umbrella, the Intel Optane technology. What we've done with that technology that we think is really important and interesting is put it into a DIMM form factor. And that one is the one that you'll hear called persistent memory, abbreviated PMEM. Like I said, it's DIMM form factor, so it slides right into your memory slots right next to your DRAM. Sits, of course, on the memory bus, real close access to your CPU. It does come in 3 different capacities, the largest one being 512 gigabytes per module. And if you look over on the side, that would give you a maximum of 4 terabytes of persistent memory per socket. And if you're used to dealing in DRAM and their capacities, that 4 terabytes is huge. You know, there's a lot you can do with that. And because the persistent memory and the DRAM coexist, if you have 4 terabytes of persistent memory on a socket, you still have 8 slots left over for DRAM. So there's a lot of flexibility there on how you kind of mix and match your persistent memory and DRAM. But in general, you've got just really large capacities to work with, which is pretty exciting, especially for those of you who are stuck with, you know, DRAM and how expensive it gets when you're looking at the larger capacities. Again, like I mentioned, this is the 200 series that I'll be talking about today, and that's very recently launched. The changes from 100 series to 200, just a few things to point out: higher bandwidth, the lower power. Then the other thing to know about this is that persistent memory has different operating modes that you can select. So memory mode is actually one of the easier ones to implement. In memory mode, you're not treating the persistent memory as persistent. It is actually your DRAM is acting as a cache for the persistent memory. So you've got kind of an extra level of large capacity memory, and it just allows you to use it, plug and play, use it just as you would regular memory. So that would be for use cases where, like I said, you're working in memory, but you want a little bit extra capacity. App Direct is the maybe more interesting one, and that's where you are actually using the persistence of that underlying media. This one does require some code changes, so it's a little bit heavier of a lift to implement, but it does also get you a lot of benefits over memory mode and storage over App Direct mode. I won't go too much into the different modes, but I do have some resources at the end if you are interested in some of those nuances. Storage over App Direct is what we're talking about for the most part today, and I'll give you a little bit more detail on what that is when we get to some of the test setup and results. And one more note is that you can actually mix and match some of these modes. There are some rules on how you can do that, but you could, for instance, have some of the persistent memory set to memory mode and some of it set to App Direct mode if you wanted. Not to confuse you further, there's the Intel Optane SSDs. I'm pointing out here the ones that are specific for the data center. There is a newer version that's fairly recent, the P5800X. This is the underlying memory media, but on the SSD form factor. So you can think of it as just a really fast SSD. Then you might have heard of the Intel Optane memory. Of course, not to be confused with the persistent memory, but this one is more client focused, and there's some options. You can use it as memory, or you can have an SSD that's kind of backed by an Optane cache. So today, for most of the talk, I'll be focusing on the persistent memory aspect, and then also we've done some testing with the Intel Optane SSD. But just so you know, there is a lot of details there. Okay, going into the software. This image is directly off of Alluxio's website, but it does obviously illustrate the orchestration piece and how Alluxio works with all these different storage implementations, as well as a bunch of the interfaces for different workloads and different big data analytics. But Intel and Alluxio have been collaborating for several years, mostly around Xeon, PMIM, and the Optane SSDs, like I mentioned. Oh, oops, sorry, just trying to move that out of the way. Okay. For this particular set of benchmarks, I worked closely with Adit, and we decided that we wanted to benchmark the TPC-DS workload using Ice Lake, some different PMIM configurations, and Alluxio as a caching layer. So if you're not familiar with this workload, it is an industry standard one, but it's based to emulate a decision support system. And it loads a bunch of tables that emulate a business that has multiple locations across probably the US, multiple stores, and those individual stores are sending some of their data back into probably the corporate office, and then the corporate office is running some analytics on all of that. So the benchmark itself models some of these queries that might be run, and also some of the data maintenance tasks that would need to be done. Most of the metrics we'll look at are in query response time, and there's some throughput metrics. There are a couple different scale factor options, and the one we'll be choosing for today is 3 terabytes. And then I've given a couple examples there. There are actually 99 queries in the TPC-DS workload. So some of them are much more simple. Others of them, as you can see, can be more complex and touch a lot more data and require some analysis like largest or smallest, instead of just picking out certain rows of a database. And then with TPC-DS, we used Apache Spark as the distributed data processing engine. This does support all of the 99 TPC-DS queries that we're using. And there's a convenient repository. This is one I found. I think there's more than this, but this allows you to get everything set up, actually generate the data for the scale factor you choose, and run the benchmark. Okay, and next I'll go into the results, including a little bit more detail on the actual test setup. So for this particular set of tests, it's all on premises. Like I mentioned, Ice Lake adoption in the cloud is still on the way. So when Ice Lake becomes available in the cloud, we'll certainly want to do some testing there. But for right now, we don't have that there. And then persistent memory actually is not widely adopted in the cloud either right now. Those are some things we're working on. It's kind of a chicken and egg situation where the cloud providers are saying, bring us workloads that run on persistent memory, and our end customers are saying, give us persistent memory in the cloud. So that's an ongoing process, but just so you know, this particular set of tests is all on premises. The compute and storage are disaggregated. Compute running on Ice Lake, these are 38 core 2-socket systems, so they're not quite the top 40 core, but they're very close. And then this is where we have that Spark workload or Spark running along with the TPCDS workload, and Alluxio's doing the caching layer on those compute nodes. The storage aspect is on an older node, a Cascade Lake node. And then the data is being stored in Minio. The different caching layers that I'm going to talk about today is Alluxio running with DRAM, Alluxio running with persistent memory in storage over AppDirect, which I'll explain, and then the caching layer running on Optane SSD. And the first two caching layers that we tested were chosen specifically because they are similar cost. And of course, this cost factor is not necessarily easy to tie down, but at the time, given the prices that we have access to, this was a similar setup to fill your system with 768 gigabytes of DRAM or a terabyte of PMEM, and then a little bit of DRAM as well. So this is, really to demonstrate that for the same cost or a very similar cost, you can have much more capacity with using persistent memory. And again, yeah, the scale factor, the data itself is 3 terabytes, and it's been compressed down to a little bit over 2 terabytes. Okay, so the results in terms of queries completed. Like I said, there are 99 queries in this benchmark, but some of them timed out. They didn't return anything. So we wanted to look at a fair comparison. The DRAM version has a smaller capacity, and that actually did impact the number of queries that were completed. And I'll go into a little bit more detail on that soon. So the DRAM version only completed 58, whereas both the persistent memory and the SSD version completed 80 of them. You can see a pretty big difference in the total runtime. This is for just those 58 queries that all 3 sets completed. And then if you look at it in terms of a time savings, you're saving about 88% of that time compared to DRAM if you're using persistent memory or the Optane SSD for this particular setup. So, I mean, it's a clear win here. A lot of that is due to the fact that DRAM has a smaller capacity, and the fact that the workload is actually running in DRAM, so that impacts even more of that capacity. And then just to look at a couple of the metrics or a couple of the queries, this was very similar to what we saw across all 99 of them, but you can see there's some where the DRAM version takes a lot longer than either of the persistent memories, and then the persistent memory and Optane SSD run times were pretty close in most cases, very small differences, but there were a few that stood out, like this query 15, where the Optane SSD actually took quite a bit longer than persistent memory. Okay, so the analysis piece. like I mentioned, there's just some differences in these different layers. The Alluxio DRAM layer, yes, there's 768 gigabytes per system, but keep in mind that the TPCDS workload is also sharing some of that DRAM, so you're not getting the full DRAM capacity for caching, meaning that you're going across network more frequently to access remote data, and that causes a pretty big impact to the workload. With both the persistent memory and the SSD implementation, your data is separate from the DRAM, giving you more capacity, fewer remote accesses. And this, as you've seen, that made a very clear impact to the performance. So what's different between these two Optane technologies? For the persistent memory storage over AppDirect implementation, what you're actually doing is taking your persistent memory that sits on the memory bus and treating it as if it's an SSD. So you're aggregating all of the DIMMs on one socket, treating it as an SSD, making a file system on it, mounting it, and then it runs just as it would if it were a traditional SSD. Whereas, of course, the Optane SSD is a true SSD and it's running on PCIe. There are a lot of similarities because, like I said, they're both using block storage. I pulled a couple different metrics here to display. If you look at the average CPU utilization over some of these queries, and I specifically ran just individual queries to measure this, it looks fairly low in the 20s or so, but then if you look on the right side at the graph of how the CPU is being utilized, there's actually a lot of variability, and there are times where the CPU is being 100% utilized in both cases here. In terms of operating frequencies, both caching layers were running at pretty good turbo frequencies above the main frequency. And I did measure both systems have the DDR running at that rate that we have certified for 3200. So here things look fairly similar, even though the Optane SSD has smaller capacity than the PMEM in this case. For a lot of these queries, I should say, the impact wasn't really seen. Where there were some differences, I mentioned, query 15, there was a significant difference between the persistent memory and the SSD layer. So I pulled a few things to try and understand where that's coming from. Keep in mind that these metrics that I'm showing here are system level, so I'm capturing both what's happening in the TPCDS workload, the underlying Spark engine, Alluxio data orchestration, anything that's happening in the system. It's all an aggregate here. In terms of cycles per instruction, there is a pretty big difference between the two. Lower is better. So the persistent memory version is able to execute, if you flip that around, it's able to execute more instructions per cycle than the Optane SSD. And that could be due to some differences in access time to that media. The persistent memory version was able to get better memory bandwidth. And that, again, could be due to a number of factors, but the Optane SSD version probably, has a little bit more latency impacting accesses to that, which then could impact what's going on in memory. For persistent memory bandwidth, obviously this isn't a metric we're capturing for the Optane SSD side of things, but for the PMEM side, there's a pretty wide range, and that again is because we're capturing the metrics at a system level, and sometimes the work is being done in TPCDS, and the persistent memory isn't being used, but there you can see it certainly is being used. And then there was also a small difference in the last layer cache miss latency. So if you are working with workloads where some of these factors, they're sensitive to these factors, then these are some things you might want to keep in mind as you're choosing your Alluxio caching layer. Few conclusions that we can draw from the work that we've done. Of course, capacity matters. The impact to performance does vary. You saw with the Optane SSD version, for a lot, it had a smaller capacity than persistent memory, but for a lot of the queries, that capacity difference did not show up in performance. So it really does just matter how much of your data you're touching, how often you need to go to remote access. In general, persistent memory will allow you to deploy with larger capacities than what you would get for a similar cost, a DRAM, which you can use to your advantage. Optane SSD has been shown to be a good option in many cases. Just depends again on how much of your data you want to be able to cache. Follow-up work that we would like to do, find some more of this hardware metric analysis and actually drill down to what's going on in the Alluxio workload and find out some more details there. And then, of course, testing that we can do in cloud environments I know is very helpful for a lot of Alluxio customers. I'll leave this slide up here for now, but there's a couple resources that you might want to check out in terms of Alluxio and Intel's partnership, the Optane technology itself, and then persistent memory in terms of how do you, as a software developer, how do you work with persistent memory? One I would certainly recommend checking out is pmem.io, and that's an industry, it's open to industry, it's not just Intel, but that's where a lot of the work has been done to define the programming models of how do you work with persistent memory. So at this point, I will end my talk and turn it over to Jasmine and Adit for Q&A.
Thank you, Ginger, very much for the great presentation. Actually, I think I've got Ben here, finally joined us. So
Great.
Let's see if Ben has collected some questions from the audience and then fired away.
Hi, Ginger. This is a great talk. Can you hear me?
Yes, thank you.
Cool. Yeah, this is a great talk. Actually, I'm very interested with the work you're doing here. I have been actually working with Intel, some of your colleagues in the past few years, working on the some benchmarking and testing about using persistent memory. So I have two technical questions here. One is really, as I understand, in this test you're doing, you're integrating Alluxio with PMEM and Optane SSD, which is exposed as a block storage. So I guess the way is you format these storage devices and use them as a file system, local file system, and then you allocate this file system capacity to Alluxio, right? So you see there's a, I guess this is a pretty standard for Alluxio, because nowadays that's the way we use off-heap storage management, how off-heap storage resource from Alluxio. So I'm just wondering, like, do you see if there's any way we can build a deeper integration instead of using like go through file system, through all this kernel and overhead? We can directly manipulate the block storage.
Yes, absolutely. And I didn't go into too many details, but I think what you would be looking at would be the app direct mode. And with app direct mode, you are not treating persistent memory as an SSD. You are actually getting cache line granularity. So it's direct access from the persistent memory technology right into the caches bypassing DRAM. And in that case, you are technically using a file system, but it's one that supports this direct access called DAX. Most file systems like ext4, XFS support this mode. And then what you're doing is you're actually memory mapping your files from persistent memory directly into CPU. So that's in app direct mode where you're going to get even more of a performance benefit because you've got smaller access or cache line granularity accesses instead of block. And then you've also got that direct pull from persistent memory right into the caches.
I see. Yeah, that definitely sounds to me a more efficient way to go with to use the persistent memory or Optane storage as the off-heap storage. Yeah. So it sounds like that's something we can definitely explore in the future to see and how much performance gain we can even get. Cool. I have another question. So in this benchmark, and actually in my previous collaboration with Intel too, we are mostly focused on TCBDS or TPCDS or high bench, this type of workloads for maybe just for, this is more for the analytics, CPU analytics, SQL analytics workloads. I'm wondering if you can also extend, or maybe this is something interesting to your or Intel team too, like extend this to like a machine learning or AI workloads, which is also very data intensive, very data hungry. Like as mentioned in the previous talk given by Lu, we are seeing for a lot of cases, we're reading a lot of data for training one model, but like we need to read this data repeatedly, and this data access pattern is very fixed. There's a very fixed data access pattern to this data. So I'm just wondering, like in this case, maybe PMAM and Optane can have also similar performance gain to this type of workloads. What's your thoughts?
Yes, certainly we were looking at some of these more machine learning focused workloads where, you know, either the inference piece or the training piece, and that's kind of on our roadmap, our collective roadmap to explore in the cloud particularly. But if you wanted to use persistent memory, again, any machine learning workload that benefits from having more local data cached would certainly benefit from persistent memory with that extra capacity.
Cool. Yeah, that's very helpful. Yeah, I don't have more questions. I think let's see if we have any more from the audience.
I think we're good. Thank you, Bin, and thank you, Ginger.
You're welcome.
Yeah, for the presentation. And then
Thank you.
Again, yeah, for any of you, if you have questions for Ginger, and she will stick around in our Slack channel if you have any questions after this talk, and then you can always find us as well. So go ahead, fire away your question and leave it on the Slack channel, like we posted there, alluxio.io/Slack.